Okay, so now what we're going to do is I've drawn the exact same lens, and what we're going to consider now is what happens when we have some object and we want to create an image using this lens. So I'm going to draw this object, we'll make it something very simple, and I'm going to put it out at say about 8 centimeters away, so it'll be far beyond the focal length. I'm going to put this about 8 centimeters away, and I'm just going to note that down here at the bottom. I'm going to say this is our object of, so we're going to call this S, and that's 8 centimeters. Okay, and so we're going to have some object, and I'm going to make it about 2 centimeters high. Now, I could just draw a line with an arrow, but we've got some other arrows, so why don't I make it just a little bit more interesting, just faintly so. I will draw a tree. Not a great tree, I'm a physicist, but a tree, just to have something to talk about. Okay, so we've got a 2 centimeter high tree here. So I'll just kind of make a note of that. And let's call this the height of the object. So we've got some height, and it's 2 centimeters. Okay, 2.0 centimeters, 8 centimeters away. And we know already that we've got a focal length is characteristic of this particular lens, and that's out at 3 centimeters away. Just going to note that here. We've got a focal length here, it's 3 centimeters. Okay. And of course that's true over on this side as well. So we're going to trace out some rays of light and look at what image is produced. So there's a few different ways that we could start, but in general we look at a couple of different special rays that trace everything out for us. And the first one that we're going to use is going to just be a line straight from the top of the object straight to the lens, and it's going to be parallel to the axis there. So it's going to be just like what we did earlier when we were looking at just the property of this lens, right? So we're going to have this parallel ray to the axis coming into the lens. Well, we know what it's going to do. It's going to pass straight through the focal point. Okay. Going from the center of the lens through the focal point and away. Okay, so that's a start, but we're going to need more information. The next thing we can do is we can send a ray right through the center of the lens, and if we send it directly through the center of the lens, it's not going to change. It's not going to refract to a different angle. So these two then give us this intersection point, which is very important. Now, we could as well do a third line to trace things out, and that's going to be through the focal point. If we pass it through the focal point from the top of the object, it's going to then end up parallel to the optical axis. So that is effectively mirroring what went on with this, and it's also mirroring what went on up here, right? Because we've got this reversibility of rays principle, and that means that we could send these rays in the other direction, and they should follow these paths as well. Just going to put arrows on all these. So if we were to send this ray back through the lens, of course it's going to pass through the focal point. Okay, so these three lines give us the ability to map out what's going on with an image of this object. So already we can kind of look at this, and I'm just going to, we know that it's upside down. That's pretty clear because it's on the other side of the axis. So I'm just going to draw this tree as best I can, So now I've got this image of the object, and we can estimate, based on our carefully done drawing here, what its height is, and we also figure out what its distance away from the I'm just going to start counting it at 15, so we're going to go out or we can start at 10, that might be easier. We're going to go 10, we're out here, so we're looking at a distance here that is just a little bit shy of 5 centimeters. So it's in between the two, we can't really tell. So I'm going to call this distance about 4.9 centimeters. I'm going to make a note of that down here. My ruler is impacting my stand for the camera. So I'm just going to say this goes out to where the object is. So this is the distance from the lens to the image, and we're going to call that S primed, and that's going to be equal to about 4.9 centimeters based on just measurements of this drawing. And then I can take a measurement here, and I get a height that is it's just a little bit more than 1. Let's call it about 1.3. So we'll get kind of an H prime of 1.3 centimeters. So these are estimates because my drawing is not perfect at all, but it gives us a pretty good sense that, one, this image is going to be inverted with respect to the original object. It's definitely going to be smaller, and we've got an estimate for what the size of the image is. And we know how far away approximately we get an image. Okay, so the next thing we could do is we could calculate what these values are with greater confidence. I'm just going to do that in this, this space here. Okay, so we can do this calculation by looking at this equation. 1 over s, which is the distance from the object to the lens, plus 1 over s primed is equal to 1 over the focal length. And we could solve this first for let's say we're going to solve for s primed because we know where we put the object and we know what the focal length is. Okay, so this can all be rearranged if we want an equation for s primed, such that s primed is going to be equal to s times f over s minus f. And in this case, we've got an s of, well, we had 8 centimeters, and we had a focal length of 3 centimeters. Okay. And then we've got an S of 8 centimeters minus F of 3 centimeters. Okay, so we get an S prime that is going to be equal to, well, this is going to be 24 centimeters cubed, no, squared, sorry, over 5 centimeters. So we end up with a value that is 4.8 centimeters. Okay, so the exact answer would be 4.8. We got something very, very close to that. So based on the diagram, that's actually quite good. Now the other thing is we could get what the height of the image produced is. And we're going to do that just underneath here. Okay, so what we know is we can look at the magnification. The magnification is going to depend on these two distances, the distance of the object to the lens and the image. So the magnification is going to be a consequence of, it's going to be minus s primed over s. And this minus sign is going to help us keep track of its orientation. Okay. So in our case, we have an S primed that is, we're going to use these values, so 4.8 centimeters over our original, I've been saying 8 centimeters, but it's 8.0 centimeters. So we've got this magnification factor that's going to be 0.6. So we get this magnification of factor of 0.6. It's negative. The negative indicates this flip, and so that means it's going to be smaller, and we see that indeed it is smaller. Now, if you want to know exactly what the size of it is going to be, well, we've got the h primed is going to be equal to the absolute value of the magnification factor times h. Okay, so then we get h primed is equal to 0.6 times the original height, which was 2 centimeters. And so the exact height there is going to be 1.2 centimeters. Okay. 1.2 centimeters, we measured 1.3, so that's actually pretty good. I mean, for the fact that we're just drawing this out very carefully, but not perfectly, I'm pretty happy with that result. Okay, so that's our basic production of an image using a convex lens.